In this video demonstration, we're going to show you how to do a very simple dynamic simulation of a plane wall system. In the last video, we went through a more rigorous derivation, and now we're going to use the equations that we developed to simulate this system in MATLAB. So in the last video demonstration, we had a plane wall with a constant surface temperature. So here we had TS1, and here we had TS2, and we took that system and we broke it up into finite control volumes where we had different nodes. So we had node I minus 1, node I plus 1. So we set up the math this way so that each node is generic, and then we can write a computer program that loops through each node from the first one to the very last one and defines the temperature derivative of each node with respect to time, and then we will have an approximate way of solving those nodes. So in the last video, we came up with an equation that basically looked like this. And this is for node I. So the change in temperature of any arbitrary node I with respect to time was equal to alpha, where alpha is the thermal diffusivity, multiplied by minus the temperature of node I, subtract the temperature of node I minus 1, and that's divided by delta x squared, plus the temperature of node I plus 1 minus the temperature of node I, and that quantity is also divided by delta x squared. So if you are confused about where this equation came from, we did just an energy balance using Fourier's law to define the fluxes coming in and out of node I. And we did that in the previous video, so go back and watch that video if you're confused about where this equation came from. Right now our task is going to be to program this equation into MATLAB and solve this. And we're going to use a simple solution method where we're going to, this is known as the forward Euler method, where we're going to say that, we're going to say that the temperature at time t plus delta t is approximately the temperature at just time t plus the derivative of the temperature multiplied by the time step. So a fairly simple approximation. And this is known as the forward Euler method. So we're going to go ahead and program these equations into MATLAB, and we'll be able to actually visualize how the temperature changes with time and distance through this plane wall. And we're going to say that for this example, TS1 is equal to 40 degrees, TS2 is equal to 20 degrees, and we're going to assume that those temperatures are constant through the duration of the simulation. Then we're going to also assume that the initial temperature, so at time 0 and for all x, that's going to be equal to 0 degrees. And if you remember from the previous video, x is changing in this direction. So we're going to use 10 nodes. So if this is the first node, and this is the last node, node n, we're going to start off with 10 nodes, and we're going to make our code generic so you can easily try more nodes to get a better spatial resolution and a better approximation to the real solution. So we're going to go to MATLAB now, and we're going to go ahead and program this in. Oh, first, let me give you a couple of more details. Sorry about that. So the wall is going to be L units thick, and we're just going to say this is 0.1 meters, so it's 10 centimeters thick. Alpha, which is the thermal diffusivity, and it's defined as, K, the thermal conductivity, divided by the density times Cp. We're going to say that that is equal to 0.0001, and we're going to want to do a simulation out to 60 seconds, starting at that initial temperature. And this is just an illustrative example. And you can certainly code this yourself and change the parameters and see how things change. My objective here is just to show you how to take that kind of a system and put it into MATLAB. So I'm just creating an M file called Euler plane wall. So first I'm just going to define my constant, so L is equal to 0.1, and that is in meters, and it's the wall thickness. We have 10 nodes. I'm going to define the initial temperature, which will be just a scalar, but we're going to multiply this by an entire vector, because remember the initial condition was 0 degrees at time equals 0, but throughout the whole length of the wall. And that's in degrees Celsius. We're going to put in our surface temperatures. And we're going to define our delta x, which I'm just calling dx. So it's going to be dependent on the variables we've already defined, so it's our length divided by the number of nodes. And that is going to be in meters. Our alpha is 0.0001. And this is our thermal diffusivity. Our final our final time is 60, and that's just seconds. And now we're going to have our time step, and we're going to go 0.1 seconds. So every 0.1 seconds we're going to make this approximation. So we do want to define an x vector. This will be useful for plotting later. So if you look at each individual node, you can see they're not just points in time, but when you plot them, you're going to need to define a point. So we are going to take our total wall, and ultimately we're going to be plotting temperature with x, so we need to define points on here. So I'm going to place those points right at the center of each node. So this first node will be dx over 2, and you'll see how we define the other nodes. So I'm going to say x is equal to, and this is going to be a vector, dx over 2 in intervals of dx all the way up to L minus dx over 2. So when we go and play this script, you can just see how x is ending up. So it's 0.005 all the way up to 0.095. So we've placed those node distances correctly right at the center of each node. So I'm going to first initialize my temperature vector. So remember, what we're getting out of this is we're going to have a temperature defined for each node. So this is, in reality, you have temperature varying continuously, but in this approximation, we're going to break up our system into discrete nodes. So the more nodes you have, the closer it gets to the continuous version of reality. But we're going to start with 10, and we can add more later if we happen to want more accuracy. So I'm going to make this a vector that is just full of ones. So this is going to be n rows long and one column, and I'm going to multiply that, and it's just going to be ones, but I'm going to multiply that by our initial temperature. So you can just see what we're going to get. Oops. Okay, so I'm storing temperature in a column vector, and you can still plot this just fine even when you're storing x in a row vector. I'm being a little bit inconsistent there, but that's fine. So this is our initial temperature vector, is just this bunch of zeros. Okay, I'm going to want to initialize our derivative of temperature, so I'm going to call this d big T by d little t, and I'm just going to say these are zeros. We're going to have a script that goes and overwrites these as it computes the energy balance for each node. So that's going to be the same size as t, so there's a temperature defined for each node, and then there's also a derivative of temperature defined for each node. So I have dt is also this vector. I'm going to want to define another vector, which is my simulation time. Okay, so now what I'm going to want to do is I'm going to create a for loop that steps through each element of time. So when I play this, and I show you my time vector, you can see it's in increments of 1/10 of a second from 0 to 60 seconds. So basically, I'm going to step through this vector, and at every time step, I'm going to recompute the temperature derivative vector, and then I'm going to use that forward Euler approximation to do this integration through time. So first I'm going to step through, I'm going to create an index variable j. I'm going to say for j is equal to 1 to the length 1 to the length of t. So it's going to go through each element of t. I'm going to want to define my temperature derivative for each element. So actually I need to do, so this for loop is going to be stepping through time, and I'm going to do another for loop indexed by I, and this is going to be stepping through by distance. So for I is equal to 2 to n minus 1. Okay, so I'm doing this for a special reason. So I'm going from, remember n was 10, so I'm looking at nodes 2 through 9. So all the interior nodes, I'm going to define their derivatives first. I'm going to do the energy balances for them first, because the interior nodes are all uniform. They all depend on the node prior to them and the node to, the node to the left of them and the node to the right of them. Whereas the boundary nodes, so node 1, it's right against this boundary, so we're going to have to input a boundary condition here. And at node n, we're going to have to input a boundary condition here. And we have the simplest boundary conditions, which are just these constant surface temperatures. But we'll have to do those outside of the for loop because they're not generic like the interior nodes. So first, let's go through this for loop and define the temperature derivative for each node. So I'm going to say the temperature derivative of the ith node is equal to alpha times minus t ith element minus t I minus 1 element, and that's going to be divided by dx squared. And then we're going to do plus ti plus 1 minus ti, and and that is also going to be divided by dx squared. And I think I'm okay here. You can always expect to have bugs here, but hopefully we're okay. So that's all I need to do in that for loop. So that's going to be going from 2 through 9, and all it's doing is it's defining the temperature derivative for each of those nodes. So within the J for loop, I still need to define my boundary nodes. So I'm going to do a special balance for node 1, but I'm going to cheat and just copy this equation and then overwrite the terms that are different. So instead of I, wherever I see an I, I'm going to replace it with a 1. And so this would be 1 plus 1, which would actually be 2. And I'm going to replace that with a 1. Okay. And then this is actually T0, but MATLAB doesn't have a 0th element. So this is actually, there's no 0th node in this case. So what I actually need to do here is put in my boundary condition. So this particular node is adjacent to this boundary TS1. So I need to replace this T1 minus 1 with T1S. And let's just make sure, yeah, that's what I called it here. I'm just checking that I'm good on parentheses. Okay, and now we're going to do a similar thing for the nth node. So instead of putting in the number 10, I want to keep my code generic so that if I ever want to use more nodes, I just go up here and I change this to 50 nodes or to 100 nodes. So again, I'm going to still my generic equation and then fill things in later when I need to. So now we're not talking about the ith node anymore, we're talking about the nth node, which is just a fixed number. So I have Tn, so the 10th node, the temperature at the 10th node minus the temperature at the 9th node. That's still valid. I'm going to put an n in there as a placeholder, and I'm going to put an n in here. So there's no n plus 1 node. Again, the nth node is right at this boundary, so it's not interacting with another node on the right side, it's interacting with this surface temperature. So I need to substitute in this surface temperature. So instead of Tn plus 1, I'm going to put in the constant that we defined earlier, T2s. And now, this loop should run and should solve for my temperature, except that at each time step I need to do this approximate integration. So I'm just going to say the temperature is now equal to the temperature plus the derivative that we just defined times dt. So at every instance as j is looping through, this temperature is going to be updated. And I'm trying to keep this particular code as simple as possible. There are certainly more sophisticated ways of doing this, but this class is focused on solving the heat equation and getting this math right. And there are definitely better numerical methods that can give you better solutions. And another thing that we're not doing here is we're not storing any of the temperatures over time. We're overriding our temperature vector at each iteration. But we can see how this responds by just plotting it. So I'm going to pop up a figure, and I'm going to plot x that we defined earlier, and t. I'm going to give this a line that makes it a little bit easier to see. So I'm going to give it a line width of 3. This is just for aesthetics. I'm going to define some axes here. So I'm going to want the x-axis to go from 0 to L, and then I want the y-axis to go from 0 degrees to 50 degrees, because our initial temperature is 0, and then the highest temperature we have is 40, so this gives us this makes sure we'll be able to see our line the whole time. And I'm just going to put in some labels here. So the distance in meters is going to show up on the x-axis. Let's see, what did I... And I'm going to put temperature on the y-axis. And And this just gives me a degree sign if I put in that little slash circ before the C. So another thing I want to do is this code will execute extremely fast, and I want to see how the temperature profile develops over time. So I don't want the code to run too fast. So I'm going to put in a little pause statement here, so this actually turns it into a nice video where it's like a frame-by-frame picture of what's happening at each time step. Alright, so let's hope this runs smoothly. I'm going to go ahead and hit plot. I'm going to go ahead and hit run. And you can see how that temperature profile develops over time. So it started out at 0 as our initial condition, and because the surface temperatures are hotter than 0, the heat flux comes in at the beginning from both sides. So the temperature starts to rise over the whole wall, and this is gradually rising. And at steady state, this is actually a really simple differential equation where it's just a straight line. So eventually, if we give this thing enough time, it will reach steady state, and that will just be a straight line. So it's still stepping through time. The reason the code is running so slow now is just because of that pause step. So it's got 600 different iterations to take. And this is going to keep popping up, so I can't really go back to my code right now. Alright, so I just killed the code. So you can see it's more or less reached steady state by the time it reaches 60 seconds. So that's how you do this. Let's just watch it one more time. So I'm going to go back in. I'll close that figure and it'll pop back up automatically. So just watch how it changes over time. It happens pretty quickly at the beginning, and maybe we can put in a longer pause so we see this. Let's put in 0.5 seconds. So our temperature is going to be uniform at 0 degrees at the beginning, but remember both surface temperatures are hotter, so that heat is going to start to flow into the wall. So actually it's hotter here on the right-hand surface, so heat's starting to flow this way and heat's flowing this way. But eventually this starts to be decreasing only, so heat's only going to be flowing through the wall this way at steady state. So this is going really slow, but this is the basic idea for how you do the simulation. There are definitely more sophisticated numerical solvers. Typically, I like to use ODE 45 or ODE 23S. Those are just a little bit more complicated to program, but really not significantly more complicated. I wanted to give you the easiest way of doing these simulations. So you can certainly go back into the code and you can change parameters, and you can give this a higher spatial resolution. So I'm going to go back to the shorter pause, and because we've written this code in generic terms of n, I can now go and give this 100 different nodes, and that's going to give us better spatial resolution. Oh, and that made it unstable, unfortunately. So there's a numerical instability here when we give it too many nodes. So let's try something a little simpler. Let's try 25. So one option you might want to do is give it a smaller time step so those derivatives don't explode. And there's still some numerical instability here. These are good examples. So let's try now and give this a smaller time step and see if it can handle 25 nodes without. So basically, a real system wouldn't do this, but when you do these numerical approximations, there are basically rounding errors that happen, and those rounding errors get compounded as you step over time. Okay, so it likes the smaller step size. So we're making a better approximation because we're taking these really small steps. But you can see the line looks a little smoother now. It doesn't have quite as many kinks in it, and the code is running slower because we are pausing now for every 1/100th of a second of simulation time. Anyway, that's how you solve a one-dimensional heat equation in MATLAB.